The PRESS program is one phase of a cooperative US-Japan program on large-scale testing of structures for earthquake and wind resistance. This particular program, which involved cooperative research between Japan and the United States on different aspects of the seismic performance of precast concrete. The final phase is this large-scale test of a 5-story, what we call super assemblage rather than a building, to see how all the bits fit together and to make sure that when we test a real building that it does what we expect it to do.
The way we've done a lot of the design of this structure is to try to make the deformations, the places where the structure has to bend and yield, make those happen in the connections between the different pieces. Now, if you're building a cast-in-place concrete structure, then there are no kind of discrete connections between discrete pieces, and you don't really have that option. But with a precast structure, you can actually do that.
We are concentrating all of the inelastic action in the connections, which is quite different from the way in which precast concrete has been designed in the past, which has been emulating reinforced concrete, trying to make it exactly the same as reinforced concrete. We're not trying to do that. We're trying to make it quite different.
The question is, how can you have a building that after an earthquake is still occupiable? That's not what people are getting now when they buy buildings that meet code, and any engineer will tell you that. These systems that we're testing here actually go a step further, and they're trying to minimize structural damage in the event of an earthquake.
To prove these new systems, the project's research tool will be the largest structure ever tested in U.S. history. It is known as the PRESS Phase 3 5-story test structure, and it will be put through the final trial in a unique facility at the University of California's Jacobs School of Engineering.
The point of this structure is to try to pull together a lot of the individual connections which have been developed over the past 5 or 6 years and tested as individual connections over the past 5 or 6 years. And the intention here is to try to pull those together in a structure and then load the structure as if it really were being hit with an earthquake, to observe the way that the connections really work when you have them in a real structure and they're all tied together and all the pieces have to work together.
The structure will actually undergo 2 batteries of tests. In the north-south direction, 4 different frame systems consisting of columns and beams will be tested. The east-west direction will test a shear wall system. This wall system is a key example of the use of post-tensioning for seismic resistance.
In the east-west direction, the earthquake forces are carried by walls. They're precast individual wall panels, so you can think of it just like a gigantic playing card made of concrete. And they're held down to the ground by what we call post-tensioning tendons. And these are essentially enormous rubber bands made of very high-strength steel. So they're not made of rubber, but they behave like a rubber band. And so you put the wall down and you have a tube down through the wall, or a duct, and you stress this steel through the duct, and essentially that kind of clamps the wall down on the ground. But if you push it hard enough, instead of something breaking, it'll simply lift off on one side a little bit, so the wall will kind of rock over like that, and then the big steel tendon down the middle will just pull it back up straight again when the earthquake loading disappears.
The seismic frame systems will all be tested at the same time. The hybrid and pre-tensioned systems form the east side of the building, and the TCY and TCY Gap connections form the west side of the structure. In the TCY Gap system, there is a small gap between the end of the beam and the face of the column. The bottom portion of this gap is filled with grout to provide contact between the beam and the column. They are connected by 2 steel post-tensioning bars which run the entire length of the building, clamping the frame together. At the top of the beam, regular rebar extending the length of the beam and through the column is grouted in, except for a short length at the gap between the beam and column. When the beam moves laterally in an earthquake, the gaps at either ends of the beam open and close an equal amount, maintaining the dimensions of the frame system. Above the TCY Gap connections on this side of the building, the TCY connections model a system that is similar to what is used in conventional cast-in-place construction. The TCY connection only uses rebar which is grouted in except for a short length at the beam-to-column interface. This connection is included since it emulates current use of precast beam connections. On the other side of the building, an innovative concept called unbonded pre-stressing is used.
Now, in previous pre-stressing of structures, normally the duct where the wire is passed through would then be grouted solid so that at all points along the length the tendon, that's the steel inside, is bonded to the structure, that's to the concrete. What tends to happen then is if you have a joint between, here's a beam on this side and a column here, as that joint opens up, it causes the pre-stressing tendon to gain a lot of strength and then go into the inelastic range. As it closes again, we lose some of the pre-stress. If the tendon is unbonded, we don't get that same increase in strength, but we don't get any non-linear behavior. We don't lose any of the pre-stress strength in the earthquake. And we've done a number of experiments which have proved this to be true on assemblages of beams and columns together, but this is the first time it's been put together in a total structural system.
Both the hybrid connection and the pre-tensioned beam, which form the east side of the building, use variants of Nigel Priestley's basic concept. The hybrid connections on the bottom 3 floors consist of beams which utilize unbonded post-tensioning strands that run the entire length of the building through a duct in the beams and columns. These strands are tensioned to clamp the frame together. Regular rebar at the top and bottom of the beam runs through the column and is grouted except for a short length at the end of the beam. When the beam moves laterally in an earthquake, the rebar yields dissipating energy, and the high-strength strands remain elastic, moving the frame back to center after the quake. Above the hybrid connections is the pre-tensioned beam system. It consists of long beams with pre-tensioning strands inside the beams, which are only bonded to the concrete at the ends. These beams are then set on one-story columns with reinforcing steel extending through the beams. As this frame displaces laterally, the unbonded strands remain elastic and recenter the structure after a seismic event. All these various systems have been carefully integrated into a structure that is designed at 2/3 scale so that it can fit in the huge Powell Testing Laboratory. Even though it is the largest lab of its kind in America, one of the challenges of the entire project is erecting the largest test structure ever built within the walls of this cavernous building. It was the charge of this man, Randy Clark, who directed a team of only 6 workers to erect the entire structure in merely 9 days.
We began the erection with the columns, and then we began to stabilize the structure by setting the beams along each floor at each elevation. And then we began setting the floor slabs. And the crew's done very well so far as to get every piece in with all the necessary parts.
The core objective of the testing is to study the structure's response to earthquakes. But how are the effects of a seismic event created inside a lab? Here at UCSD, the cadre of seismic design and testing experts has the ability to employ a technique called PseudoDynamic Testing to faithfully recreate the effects of an earthquake.
The reason that we can slow the earthquake down in this form of testing and still have valid results is because we ensure that the sequence of displacements that we put on to the building is the same as would happen to the structure if it was tested at a faster speed, in other words, at the correct loading rate for the earthquake. And damage is related to displacements rather than forces or anything else. So if we take it to the same displacements that would happen in the real earthquake and in the same sequence, then we get the correct levels of damage. In fact, we get slightly more because it's more severe on a building to hold it at the large displacements for a period of time than it is just to achieve it for a fraction of a second and take it off. So it's slightly conservative, but it is realistic.
The simulated seismic events for the pseudodynamic process are derived from a select variety of actual earthquake records, among them the 1940 El Centro earthquake record. These records are then modified to ensure that the structure is thoroughly subjected to the required levels of seismic intensity and beyond. The mechanical means which will bring the earthquake record back to life are the actuators.
For this particular test, we have 10 different actuators. We have 2 at each floor level. They come in different varieties with strokes from plus or minus 6 inches for the first floor, all the way up to plus or minus 24 inches for the top floor. The actuators on the first floor have a 165,000 pound load capacity. Those at the top floor have a 220,000 pound load capacity. This actuator here, for example, can push with a load of 165,000 pounds. That's something around the weight of like a 727 or a 737 jet aircraft. The actuators are kind of unusual in that we have this combination of really large forces, but yet we're able to control them down to very, very small displacements on the order of 1,000th of an inch. In the control room during the test, there'll be 5 of us. There'll be me. I'll be controlling the actuators and monitoring the health of the actuators and the data acquisition systems. There'll be Sri. He's monitoring what's actually going on during the test and conferring with Dr. Priestley to make decisions about what we're going to be doing next, whether the structure is behaving as we want it. There will also be 2 graduate students, Jim Conley and Stefano, and they will be doing close to real-time analysis of what's going on in the structure. The test actually takes place in several intermediate tests, and between those tests, these 2 graduate students spend a lot of time helping us make decisions about what we want to do on the structure next.
The structure is ready for testing. 12 years and countless hours of design and preparation have gone before. The testing begins. Time-lapse footage compresses the process. The team watches closely, monitoring the activity of the actuators as well as the response of the structure. A graphic display shows the amount of force the actuators are exerting to produce the target displacements. As it is subjected to the first loads, the structure makes evident its response to being displaced.
I think it's probably the pins, I guess, is it?
Something slipping in the pins, I think. Yeah. Okay, just hold it there for a minute.
The structure successfully withstands the design-level earthquake requirements.
We are right on.
Now it is crunch time. It will be taken to the extreme. The displacement will be equivalent to an earthquake which might occur once a millennia. The top floor of the building will move over 11 inches from center, or over 22 inches back and forth, much greater than the movement which occurred in only a few seconds in El Centro in 1940. A few seconds which had devastating consequences. Here, the duration is a matter of hours. Yet the structure is actually subjected to more stress than in that real seismic event. As the test progresses, displacement becomes clearly evident. The flex plates in the walls bend as designed. The top floor moves further and further from center. The columns clearly leaning. At the height of maximum displacement, the researchers clamber over the structure. Floor by floor, they inspect and record evidence of the displacement's effect, so they can later correlate it with the data gathered by the instruments.
Yeah, we got the torsional crack in the floor.
You got a torsional crack now?
In the floor, yeah.
0.1 millimeter. Look at you, too excited about that.
Big fire?
Time-lapse footage reveals how the pseudodynamic testing process eerily recreates the earthquake. The building experiences the first seismic wave, and then suffers a remarkable displacement, and continues to sway with subsequent seismic waves. But the walls, frames, and floors stand, and by all accounts, don't even approach a loss of integrity.
The lack of damage has surprised even me. It's been less than I expected, so it's just been great. It's a superb test.
It's amazing to me how little damage, how little distortion, things are able to move the way they're supposed to without anything bad happening. And if you had this kind of an earthquake and you're going to run out into the street probably when it's over, you're going to come back in and see architectural and interiors type damage, but the building structure is going to be fine and you'll be able to go right back to work. And I think that's amazing for an earthquake this size on a building.
There's no doubt that the level of shaking represented by what we've put onto this building is well above the design levels for buildings in California.
But it seems that the performance we're seeing at this displacement is actually much better than I'd even dreamed. Some of the very critical connections seem to be performing absolutely perfectly, and places where I expected to see some cracking in the concrete, I mean, not dangerous, but at least cracking, we don't seem to be seeing it. So the building is doing just astoundingly well, as far as I can see. And I'd be very happy to live in a building like this in a big earthquake. What else can I say?
Next in line for the battery of tests are the 4 frame systems joining beams and columns that make up the east and west sides of the structure. After shakedown and calibration, the researchers are ready to get underway. The first tests take the structure up to a level 2 earthquake record, equal to events which might occur once every 50 years. The various framing systems are performing well. This time-lapse footage clearly shows not only how flexible concrete can be, but it once again illustrates how effectively the pseudodynamic process recreates the dynamics of the earthquake record. The researchers then take the structure to the 500-year seismic event. The top floor is displaced about 10 inches from center, giving the structure a tilt which is clearly evident, even to the casual observer. The structure easily survives the design level tests. Nigel Priestley comments on what is yet to come.
The next step in our testing, which will start next Tuesday, is to take the structure to levels of seismic displacements which are significantly bigger than expected in the design earthquake. The structure is designed for a maximum drift of 2%. What we want to do now is to take it to 3% drift, so a margin of safety of something like 50% above the design displacement, and see how it performs at that level. Assuming that it performs well there, we'll then take it up to 4% drift, or twice the design level. If it's still standing and intact at that stage, we'll call it a day, because we won't be able to apply displacements any bigger than that. We've run out of capacity in our actuators.
At that 3% drift, or 50% above the design displacements, the top floors are pushed close to 12 inches from center. At this level of displacement, well beyond what the framing systems were designed for, the various systems start to show their superior performance characteristics. The pre-tensioned beams and hybrid systems perform extremely well, without an increase in significant damage.
So it's close to 7/16 inch crack, and I think as I said earlier, it's all concentrated here, and you don't get any crack on the beam at all. So it's performing as it was expected.
As in all good research, the team wants to probe the limits. They follow their plan to take the structure to 100% greater displacement than the design level. The top floor will be displaced 18 inches from center, the kind of displacement which might occur once every 2,500 years. The test gets underway. The researchers watch closely, monitoring the actuator systems and state of the structure. At the extremes of displacement, the team inspects the structure.
There's quite a lot of relative movement there.
Diagonal shear crack on the joint, the exterior joint.
These welds all look okay.
HE3S, one of the bottom rebar fractured.
Outside of it.
Outside one.
The test continues. As the strains increase, the structure responds with eerie creaks, cracks, and booms. The structure is reaching phenomenal displacement. The joints, where by design the stresses and damage are concentrated, start to show some effects. Concrete spalls, crushed at the joints between columns and beams. Rebar under tension snaps like immense rubber bands. Then, on the second full cycle of drift, something happens. Judiciously, the test is halted. The structure is allowed to settle.
Yeah,
I could fire those guys up and let them come to zero load.
Let's do that.
All right.
As far as, the test's completed now.
The team has taken the test far beyond the limits of expectations, into a realm which few structures have entered, and remained standing. After the structure is cleared of apparatus and instrumentation, project scientist Sri Sritharan takes the first step to understand what really went on in the test structure, revealing the effects of the seismic stresses as well as the performance and resilience of the designs.
The only damage that occurred to the wall system during the wall direction testing was just spooling of cow concrete in the corners here. You could just patch it up if you wanted to, and you're ready for the next earthquake. There were some minor cracks that we marked here that opened up and they closed when we removed the load. On this side we marked all the cracks, and if we take a look at it on the other side, you will see there is no damage that you could visibly see. Right now we are looking at a hybrid joint system where the column to beam connection is established with unbonded post-tensioning, similar to what we have seen in the wall system. You could see there's no damage to the joint region where the maximum forces are transferred through. The damage what we see here at the top and bottom, in a design level earthquake we will not see any damage like that. Part of the reason why we see this damage was that we took the structure to much larger displacements. At one point we moved the top of the column by 18 inches, and that's the reason we see some damage. And again, this is not structural, so we could easily patch up this damage as well. We are now looking at a pre-tension frame connection. Unlike the other precast system that we have looked at, here the beam is continuous, which contains the joint as well. So it runs from one end of the frame to the other end. In this system, the crack was supposed to develop between the joint and beam, even though the whole piece was constructed as one segment. And that's exactly what happened during the test. And you can see the crack develop right at the interface, and the crack opened up all the way to 3/8 of an inch for the maximum earthquake load being imposed onto the building, and now it's almost completely closed.
The success of the PRESS program has been a defining event, which promises to propel seismic engineering, design, and science forward.